Welcome to lecture 16 of EfficientML.ai. So today we are going to learn about the efficient diffusion models, how to accelerate diffusion models. In the previous lecture, we've briefly talked about deep generative learning. So we first train a model, and then we can predict the data distribution. So different from discriminative model, which is to predict this decision boundary, the generative model tries to predict the distribution of the data. So there are lots of applications for generative model. For example, photo editing, image generation. You may use Midjourney to generate images, and OpenAI Sora can generate videos as well. But all these generations are pretty computationally intensive. So in this lecture, we are going to learn about how to make these algorithms more efficient and much cheaper to run on the hardware. So this is the landscape of deep generative learning. We've previously already covered the generative adversarial networks. We've also talked about the hard autoregressive model using token in, token out approach to model that. Today we are going to talk about diffusion models. We also introduce efficient autoencoders. So this is the landscape of deep generative learning. So here's the agenda for today. We are going to first talk about the basics of diffusion model. In order to accelerate it, we need to first understand how diffusion model works, including denoising, conditional diffusion models, latent diffusion models, image editing, and personalization. Next, we are going to introduce fast sampling steps, the VDM method, distillation method, and also acceleration techniques using sparsity, quantization, and also multi-GPU parallelism. And the figure on the right-hand side is the model Sana developed by ourselves, and showing a cyberpunk cat with a neon sign that says MIT. Okay, so let's first introduce how diffusion model works and diffusion model basics. So there is two concepts. One is the forward diffusion process. The other is the reverse diffusion process. So during the forward diffusion process, we try to add noise to the data. So the data becomes noise. In the reverse process, we gradually denoise and release and reveal the data. So this can be illustrated in this image. The first is the forward pass. The second one is the reverse pass. You can see in the forward pass, we are trying to destroy the data by gradually adding a small amount of Gaussian noise. So originally, the image is two different distributions. Now it becomes the noise. And during the reverse process, we are trying to create data by gradually denoising the noise from a stationary distribution. Finally, we converge to reveal the original image. So this is a multi-step process. Okay, so the forward process is basically adding the noise. Okay, starting from the data across many steps, then it becomes a noise. And the XT is actually dependent on the previous step. Okay, so it's a Gaussian distribution with the mean of, this is the mean, is related to xt minus 1, the previous step, and the variance is a Gaussian noise. So this beta t is predefined to control the diffusion speed. So this is the relationship between t and beta t. So that's the forward process. To add noise, we get a relationship between xt and xt minus 1. And then what about sampling xt directly from x0, from the original clean image? How do we get the noisy image at time step t? So this is a long derivation, but actually it's quite simple since this xt is linearly related to xt minus 1. We can define alpha t to be 1 minus beta t, so we can rewrite the equation like this. This is a relationship between xt and xt minus 1. We can expand this equation by inserting the same relationship between xt minus 1 versus xt minus 2, so that we can represent xt with xt minus 2, epsilon t minus 2 and epsilon t minus 1. Okay, so adding two different Gaussians, we have this property so that we can combine these two terms, the noise term together. So we get a relationship between xt and xt minus 2. On and so on, we can all the way get a relationship between xt minus 1, minus 2, minus 3, all the way to x0, and with the combined noise. And we can shorten that by defining the alpha t bar to be the product of all the alpha I. And as a result, we can represent xt as a relation with respect to x0 plus the noise. Okay, so this is the mean, and this is the variance. So now we have the relationship between the original clean image, which is x0, and then at each time step t, what is the xt? So we define this relationship between xt and x0 as the diffusion kernel. Okay, so for sampling, xt equal to the relationship between x0 and the noise. Okay, so beta is designed such that when alpha t close to 0, the distribution is close to the normal distribution. So given at any time step t, now we can represent that as a function of x0. So that's the forward process, gradually adding noise. We can define any time step respect to the first time step 0. And now we are going to talk about the reverse process, the reverse denoising process. Starting from xt, we want to obtain x0. Okay. So when beta t is small, the relationship between xt minus 1 and xt, so the adjacent two steps, is also a Gaussian. Okay, so this is the mean, which is learnable. Basically, that's what we are trying to predict, consuming the majority of the computation flops, given xt to get the mean, and the variance is also a Gaussian. So let's see in practice, how do we finish the training? So given a clean image, okay, this is the clean image, which is x0, since we have the relationship between x0 and xt, so xt basically equal to x0 plus the noise. So x0, this is scaling factor plus the noise, because it's scaling factor. So square root of alpha t, square root of 1 minus alpha t, which is exactly the same here. And the epsilon theta is the neural network model predicting the noise. Okay, so we add them together, we get the xt, and then we pass it through the model epsilon theta to predict the noise, okay? To predict the added noise. And this is our predicted noise. This is the noise that we originally added to x0, and then we try to match the predicted noise with the original added noise so that we can have a MSE loss right here. I try to match them together. So that's basically the training process. So, although the equation is pretty complicated, if we draw it in the figure, it's actually quite simple, right? So we sample a t, and then we can sample x0, sample image, and maybe a cat, maybe a dog, and then we sample a noise from the Gaussian distribution, and then we add them together by having them sum up together to get xt, and we predict the noise given the xt. Okay, so epsilon theta is given the xt. We try to predict the noise, okay, and try to match the noise that we originally sampled. So that's how we add noise to the training process. Okay, so basically the training part is trying to predict the noise, make sure the noise match the noise we inserted to the image. So that's the training algorithm. What about inference? What are we doing during the inference time? So given a noisy input at xt, okay, so we pass it through the model epsilon theta. So what are we trying to predict? We are trying to predict xt minus 1. Okay, so we already have the relationship between xt minus 1 and xt. So this is the mean, this is the variance. The mean, we are trying to predict that by using this equation. Okay, so mu theta is a combination of xt and epsilon xt. Okay, so it's a combination of xt and epsilon xt. So epsilon xt is basically predicting the noise given this input. Okay, so given this input, the model epsilon theta is predicting the noise. What is the noise inside this image? And we subtract the noise. This is subtract. We subtract the noise from the image. These are the scaling factors. We subtract noise from the image. We get a cleaner image. Okay, a cleaner image is added with a noise, and then get the denoised image, xt minus 1. Okay, so in that way, we complete one iteration from a noisy input image, a noisy image xt, to get a cleaner image xt minus 1. Okay, the rule of thumb is denoise. We first predict the noise. Okay, predict the noise using the epsilon theta. This is the model. This is the majority of the where the computation goes. Predict the noise, subtract the noise. Okay, and here it actually added another noise, another Gaussian noise. Since xt, this is the mean, this is the variance, and we have to add back this noise to get a denoised image. So that is just one step of denoising from a noisy image to a cleaner image. And then we can repeat this process to get xt minus 2, xt minus 3, all the way to x0. Okay, so that's the entire denoising process. Different from the previous models where it's just one time. Now we have to run the same model iteratively. So this is where the majority of the computation goes. So it's dense prediction. You have to make pixel-wise prediction, not just a class, not a bounding box, but you have to make pixel-wise prediction. That's why this model is usually pretty heavy and taking the majority of the time, making it slow. Another reason it is slow is because we cannot do it using just a single step, or very hard to do it in a single step. But actually, we need a lot of steps. That's why it makes it slower. So these are the generated images, actually outperforming GANs on the ImageNet dataset. So it's a pretty good result, pretty good start. Okay, so now let's talk about conditional diffusion models. We don't want to just give a random image, but we want to condition the generation on either a class. For example, we just only want to generate a cat or a dog, or text condition. For example, a sequence of text tokens, like photo of a moon gate. Sometimes we also want to add the pixel-wise conditions. What is pixel-wise condition? So given a spatial map, like a segmentation map, a cat, or a canny edge, the edge of a cat. Okay? So we not only need to provide a time step, but also add a condition to the model. So let's see, how do we perform conditional image generation using diffusion models? So one idea is to use this scalar condition, very simple spatial addition. So this is the original feature map. This is the conditioned feature map. How do we condition that? Given a class ID, like a cat, maybe ID number 776. And then we encode that by passing it through several multi-layer perceptions. And then we get an embedding, batch size times C. C is the channel, versus the original feature map is BCHW. So we broadcast the single element to H times W, and then we perform this broadcast add to add them together to get a conditioned feature map. So that's how we add this class condition. We can make it a little more complicated, right? For example, we can pass it through a larger MLP to get two parts, B times 2C. Okay, one is a scalar, one is the bias. So we scale the feature map. We can also add to the feature map to get the condition, the feature map. That's another way to add this kind of scalar condition. Okay. How do we add the text condition? Now we have two modalities. One is the image modality, the other is text modality. So during visual language model, like the VLA we discussed in previous lectures, we find it's possible to project image and language, both of them into tokens, right? And as a result, we can use cross attention to combine image and language. For example, the input feature, we divide it into several patches. Each patch is a token, so we can tokenize them. So for the text, we also pass it through the QKV matrix. Okay, so we get the Q token, query token, T token, and the value token. Okay, so we first do QK transpose. So QK transpose, we use that to the weighted sum for the output token. So the final dimension, token dimension is still the same as the query, which is the number of image tokens. So the output result is still an image. But that already included the information from the language. Okay, so that's one way to add text condition, insert the text condition into image generation. There's another way to do joint attention. So in the previous method, are they symmetric? Actually, language and image, they are not symmetric. So the image is treated as the query. The language is treated as the key and the value. So the language and image, they are not symmetric. But in the joint attention, the language and the image, the image feature and the text feature are actually symmetric. So they are passed through independent QKV transformations. So this is the QKV transformation for the image. This is the QKV transformation for the language, for the text. And then we concatenate them after the transformation. Okay, so this is the query from the image feature. This is the query from the language feature. We concatenate them together to get a combined image text feature for the query, combined image text feature for the key, combined image text feature for the value, and we feed them together to the attention. Okay, and after we get the output, we split it by passing them through different output transformations. So there's QKVO for the O. We also have independent WO for the image feature and also for the text feature. So on the right-hand side is another diagram showing this relationship. So image and text, they are passed through independent QKV transformations and then concatenated together to form joint attention and then split it to separate WO matrices to perform NLP and for the next layer. What about totally combining them together early? So this is another approach, a single self-attention to combine the image feature and the text feature, the text condition. Okay, so the tokens are early concatenated before we feed them to the QKV transformation. Since the image feature and text feature are concatenated already, so we can feed them to the same QKV transformation. Okay. And after we pass them through the attention, we have a single output transformation. So this is the early fusion for the image and the text feature. We can also perform pixel-wise condition. Okay, we've talked about class condition, so using a class. We talk about language text condition using a sentence to describe what you want to generate. Now we want to do pixel-wise condition. For example, we want to generate something that follow the edge described here. This is using a tiny edge detector to find the edge. As a result, the generated image together with a text prompt can exactly follow the edge from here. We can also use input human pose, and input human pose extracted from here. This is the head, this is the body, the hands, and then we can generate several images and the chef in the kitchen following exactly the same human pose, or even a Lincoln statue following the exact input human pose. And that is by using ControlNet, which is a new technique published last year to add the control by conditioning it on pixels. So how does that work? So this is how ControlNet works. Previously, we have a neural net given noise, we can predict the image. Now we freeze the original network, but we make a trainable copy. And we insert the condition for the trainable copy, started with a zero convolution, so that when the training starts, this branch has no effect, since this is zero convolution before and after. Okay. And during the training, they start to change. We make the trainable copy. We call this part control net. So this part is controlling the main branch. So we have two branches. Control net controls the main branch, and the main branch is locked. The control net is a trainable copy of the original branch. These are zero initialized one-by-one convolution, such that the training is very smooth. The starting point is basically equal to nothing is on this branch, and we only have this locked pre-trained model. So let's dive one step deeper to expand that image. So we add these pixel-wise conditions from here on the right-hand side. It could be either the semantic mask, any edge, whatever pixel-wise information you want to insert. And we keep the original condition, including the text prompt and also the time step. So that's the original condition. We copy these down sample stages. So these are the down sample stage. We copied the condition control branch from the original branch while we are freezing all the layers of the original branch. And then for the upsample part, we just pass it through zero convolution. So we only copied half, only copied the encoder block, but not the decoder block. Okay. So this is how we add the pixel-wise condition beyond the text condition and also the time condition, which has been added to the original branch, which is frozen. And this condition is also inserted at each encoder stage of the control net branch. Okay. So there's another technique, classifier-free guidance, which is try to trade off between the diversity and also the fidelity. Okay, so to condition on some class, we are trying to, given this class, we try to predict what is the image. But we can also train another classifier, okay, given the image, try to predict the class. We want to make sure the class is exactly the one we want to generate. Okay, so we can add the classifier gradient during the sampling. Okay, so make sure the sample is classified as C. So we not only want to run this generation model, but also we want to run this discriminant model, make sure the generated image is exactly belong to the class. So the new sample distribution is defined in this way. So given this class, we want to sample an image, and also this image is also predicted as to be belonging to class C. And we add omega to the power of omega, which is the guidance strength. In the log space, the multiplication becomes the sum. And to the power of omega becomes omega times log p. Okay, so that's why we add omega to the power place. So this is basically the naive comparison between naive conditional sampling We have condition here versus classifier guided sampling, which is adding another term. So given this image, we want to classify the class and make sure that belongs to C. So this is the classifier gradient, and the strength is controlled by this guidance strength. So that's the classifier guided sampling. So this is comparing a small omega versus a larger omega. A very small omega, the generated image is sometimes confusing. It is not dog, but on the right-hand side, the fidelity is much better. So larger guidance of W lead to better quality, but less diversity. So the diversity is very poor, versus here it has many diversities on the grass and in the snow, but here the diversity is much poor. So what is the limitation here? By using such classifier guidance, we can only work on class condition. Okay? There's no text or pixel-wise condition, since we have to predict the classifier. And we need to train an additional network, which is a classifier network, which is cumbersome. Can we just use one network and and don't have to train a separate classifier network? So that's the classifier-free guidance, a very widely used technique these days to support diverse conditions, including the class condition, text condition, pixel-wise condition, etc., without using an actual classifier network. So this is the original term defined in the classifier guidance as two terms multiplied together. One is given the condition, predict the image. The other is given the image, make sure it belongs to class C. Omega is the strength. We can apply a Bayes rule, okay, such that this term, given the xt with the probability of the condition, we can rewrite it to be given C with probability of xt versus pxt. Okay, so this is the condition model. This is the unconditioned model. And putting them together, that's Bayes rule. Bayes rule. So basically, we can run the inference twice. One is the conditional model. The other is the unconditional model. So in that way, we can rewrite intuition on the top by inserting the pc given xt to be pxt given c divided by pxt. And to the power of omega, we still put it here. And we find these two terms can be combined together to the power of omega plus 1. So we are combining these two terms together since they're the same. So we have omega plus 1. The denominator, we just move them together, move them to the right to the power of omega. So in the log space, this division becomes a minus, okay, subtraction. So we have omega plus 1 log pxt given c minus omega log pxt plus this condition, okay, plus c. So what does that mean to the original model? Okay, previously we are having the condition and the t right here. Now we just replace it with two terms. We inference it twice. Okay, one is given the t and c. The other is given only the t, no c. So we have to run the inference twice. Okay, combine the results of the conditional and also the unconditional forward. And what does that mean? We need to double the flops. Okay, do it once with the condition and do it another time without the condition. So that's basically the classifier-free guidance. And let's see how that works. So on the left-hand side, there is no guidance. This doesn't look like a dog, but on the right-hand side, it looks like a dog. So larger guidance W is also leading to better quality, but less diversity. But advantage is that it can generalize to any condition forms, not just a class condition, it can generalize to different conditions, like pixel condition or text condition. And we don't need to train a separate network. We don't need to train a classifier. Okay, just the same diffusion model. We just need to run the diffusion model twice. So all the techniques we learned so far are gradually adding complexity, making it more computationally expensive, like adding a condition, etc. And later we are going to talk about how to reduce the computational flops, starting with latent diffusion models. Imagine you have a pretty high resolution image, which means when we are predicting the noise, we have to make pixel-wise prediction. That's a lot of noise pixels to predict. Can we pass it through an encoder and then denoise at a smaller resolution, like 1/8 or 1/4 the resolution, so that you can have a much smaller compute? Actually, that is a very widely used technique these days, called latent diffusion. Okay? Rather than directly do diffusion on the high resolution image, we first pass it through a encoder to downsample it by 4 times, 8 times, even 64 times, as our recent work called deep compression autoencoder. So we have a much smaller latent space, and you do diffusion in this smaller space, which is much easier and much faster. And after you denoise, we pass it through a decoder, okay, to reconstruct the original image. So the diffusion only need to run in this smaller resolution latent space, rather than on the high resolution original image space. So that's a way to compress the image and only run diffusion in the compressed space. And that is called latent diffusion. Okay, only apply diffusion on the small resolution part to enable simpler denoising and also faster synthesis. And let's see how that changes our roadmap. So this is the original configuration. The difference is that the image is fed to an encoder, and we feed the encoder's result as the Z. Okay, so we first added the noise, okay, latent space, added the noise. This is the sum, pass it through the model and predict the noise and try to match the noise. Okay, so the learning target is exactly the same. The only difference is that we added another term rather than directly feeding x0 to here. We feed x0 to an encoder and get z0, and feed the z0 to the model to predict the noise. And z0 is in the latent space, has a much smaller resolution. So this is during the training, the forward. What about during the sampling and sampling time? So everything is actually the same except for the last one. We want to feed it to a decoder to decode the original image. So previously we have this xt, and then we pass it through the model to predict the noise. And we subtract the noise from this xt, and we do denoise. Denoise, we added another noise to get the final denoised zt minus 1. So this is from zt to zt minus 1 all the way to z0. And after we get z0 in the latent space at a smaller resolution, we pass it through the decoder and reconstruct the original image. So the only change is the right part. The decode passes through a decoder from low resolution to high resolution. Everything else stays the same, but we can now generate much complicated and higher resolution image. Like here, an astronaut in the jungle, code color palette, and here is a deep sea diver floating. This is Stable Diffusion XL for high resolution image generation. As you can imagine, the more we compress, the less the workload, the smaller the number of resolution, the smaller the number of tokens. So recently we invented this deep compression autoencoder. Rather than compress the token by 8 times, we can compress it by 64 times. What does that mean? It means 8 times more compression in each side, and altogether you have how many fewer tokens? 64 times fewer tokens, because H times W, two sides. So 64 times less tokens. And how does that impact the attention's complexity? 4,000 times less flops, right? Since the attention computation complexity is quadratically related to the number of tokens. We are reducing each side by 8 times, so altogether 64 times less tokens and 4,096 times less flops. Okay. So this is original stable diffusion's variational autoencoder, VAE, reducing the resolution by 8 times, passes through the diffusion model pretty slow. This is our proposed approach using deep compression autoencoder, 64 times compression on each side, passes through diffusion model, and make it much faster. However, this is not straightforward. Naive approach, for example, SDVAE, under 64 times of compression, the quality is very poor. But using deep compression VAE, the quality is much better. On the left-hand side, we are comparing the compression ratio. The higher the compression ratio, the more preferable, but the harder. Baseline methods, SDVAE, the FID deteriorates very rapidly. But the deep compression autoencoder stays very stable. FID even given 128 times compression ratio. And how did we achieve that? So reducing the resolution, you have a very naive approach, right? You can directly move the information from spatial dimension to the channel dimension. Say every 2 by 2 pixel, 4 pixels. You can change it from 2 times 2 times 1 into 1 times 1 times 4. So that's the explicit transformation from spatial to channel. Okay, so by explicit spatial to channel, we can add this explicit spatial to channel branch to the downsample block, and add this explicit channel to spatial branch to the upsample block. We call it residual autoencoding. So rather than using the many weights to learn such stuff, we use this zero weight branch, zero weight branch as a residual bypass to learn this. And we find adding this residual autoencoding makes it a lot easier. For example, the RFID without residual autoencoding will deteriorate very fast in F64, but it remains very stable under a high compression ratio. A second technique is this 3-stage adaptation to high resolution. So we want to deal with high resolution like 4K by 4K image generation. So how do we have a autoencoder to support so much higher resolution without requiring a lot of training flops? So we decoupled it into 3 phases. The first phase, we just perform low resolution, train the whole, both the encoder and the decoder. Okay, given an input image, encoder encoded into a latent space, and the decoder reconstructed to the original image. Okay, so this is low resolution, full training. And in the second step, in order to save the computation, we perform high resolution latent adaptation only to the middle layer. Okay, so the middle layer corresponds to like classifier's last layer. Only tune these middle layers and freeze the remaining layers. And finally, we added this gap loss to further polish, to do some refinement only on to the last layer of the decoder, since that's only related to the low-level features. The low-level feature is actually refined in the last stage. So we do such layer-wise sparse tuning, not tuning all the layers, but sparsely tuning the middle layer or the late stage to save the computation and make it very fast to train such a autoencoder. So using this autoencoder, we can greatly accelerate the image generation diffusion models. So this is using the original latent space, the STVAE, which is 8 times reduction. So it's pretty slow. It generates only 17 images per second. But on the right-hand side, we are using the 64 times compression. Okay? F64 reducing the number of tokens from reducing the resolution from 512 to 8 by 8. Okay, so we can diffuse on only 64 tokens, compared with previously we have to diffuse on 4K tokens. So it's a lot faster, 19 times faster actually, compared with using the original autoencoder. So autoencoder matters a lot. If you can apply such deep compression autoencoder, you can have much fewer tokens and quadratically reduce the computation flops for inference of diffusion models. And another benefit is that now we can achieve high resolution image generation without using a lot of compute. For example, 4K image generation. Look at the shape. Look at the details, how much detail it has. Okay, this is 4K by 4K generation. And compared with 1K, this is astronaut in the jungle. The 4K has a lot more details, but a lot more computation if you don't use techniques like deep compression autoencoder. So based on deep compression autoencoder, we built a efficient image generation diffusion model called Asana, which takes advantage of several factors. One is the linear DIT module, using the linear attention that we previously described. For high resolution, we have a lot of tokens, and the computation complexity grows quadratically with the resolution. So a linear attention will be very feasible, will be very helpful to generate high resolution to achieve speed up. So this is using the linear attention. This is using the linear DIT module, using the deep compression autoencoder. And here is using a modified complex human instruction, which we are going to talk about that. So previous diffusion models are using an encoder-decoder model like T5 as text encoder. So we think recently there's a lot of progress of decoder-only large language model like GPT model, GPT-2, GPT-3, 3.5, everything after that, for Google's Gemma. Okay, so can we use this decoder-only model as a text encoder? For example, given an input to the Gemma, a man is walking. The Gemma's output focus on conversation. It says, "This is a great start. To make this more interesting, tell me about the man and his walk. For example, where is he walking? A busy city street? What is he carrying? What is his mood?" The more details you give, the more vivid and engaging the story can be. So this is not quite related to image generation if we naively feed our prompt to Gemma. It is not basically related to image generation, but focusing on conversation and storytelling. In contrast, we add a complex human instruction, append this fixed human instruction before the actual prompt. A man is walking, and now Gemma can give correct output, saying a man in a worn leather jacket walks gracefully down a cobblestone street, his head downcast, his silhouette framed by the setting sun. He wears a faded blue scarf around his neck, etc. Give very detailed description beyond the simple instruction we gave. And how do we achieve that? This is using the prompt engineering we discussed in the previous lecture. So this is the complex human instruction we feed to Gemma. Okay, not only the example, not only the prompt, but also the example for in-context learning. Given a user prompt, generate an enhanced prompt that provide detailed visual description suitable for image generation. Evaluate the level of detail in the user prompt. If the prompt is simple, focus on adding specifics of colors, shapes, sizes, textures, and spatial relationships to create a vivid and concrete scene. If the prompt is already very detailed, refine and enhance the existing details slightly without overcomplicating. We also give some examples. User prompt, a cat sleeping, we converted to enhanced version. A small, fluffy, white cat curled up in a round shape sleeping peacefully on a warm, sunny windowsill, surrounded by pots of blooming red flowers. Okay? By using the in-context learning example with two user prompts. And finally, please generate only the enhanced description for the prompt below and avoid inputting any additional commentary or evaluations. Okay, followed by our real human prompt. A man is walking. Okay, and in that way, we can let this decoder-only language model to give the output that is preferable for the diffusion model to consume. Okay. All right, and how does it echo with the visual language model that we previously discussed? For example, the VLA visual language model. Actually, we can use VLA to recaption the image. So given the image, we want to, this is the original caption, which is actually very short. Top view written Happy Valentine on a card, chocolate cake, like good background. Very simple, right? But using VLA, our visual language model, it can give very detailed caption. Like this is VLA 13b. The image captures a delightful scene of a Valentine's Day celebration. At the center of the image is a round chocolate cake, rich and inviting. The cake is adorned with a red heart on the top, symbolizing love and affection. The words Happy Valentine's are elegantly written in red icing on the cake, adding to the festive atmosphere. The cake is placed on a wooden table. It's indeed a wooden table, which provides a rustic charm to the setting. So you can tell it's a very detailed description that is unlikely to be labeled by a human labeler to give such a detailed and fancy label without hallucination. So this is the 13b, this is 3b. We feed it to different sizes of VLA to vote based on their clip score to prevent hallucination and try to find the best match. Clip score basically measures the similarity, the relationship, how well does it match between the caption and the image. So now everything begins to converge by using our visual language model, the VLA. We can generate more data. We can use the data to train better SANA. So SANA and VLA can grow together. So that's the beauty of such co-design. All right. Now we have to build the SANA based on the above techniques. We can accelerate SANA. We can accelerate 1K image generation by 25 times, accelerate 4K image generation by 100 times, compared with the Flux Staff, which is a popular diffusion model these days. So this Flux, this SD3, PixArt, SANA, okay? And where is this 106 times acceleration come from? So it comes from deep compression autoencoder, linear DIT, kernel fusion, and also using the flow-based DPM solver. And the quality-wise, Zhang evolved previously, and this is for the Flux model. This is for the SANA model. They are almost neck and neck. Let's see some generated results from SANA 1.6b. The text, the logos, and the human face, actually a lot of details. And here are some more examples, like a blue Porsche 356 parked in front of a yellow brick wall. Here, this one is probably more interesting. An avocado wearing a royal crown and a robe, seated on a throne in a grand, opulent setting. The scene is surrounded by other avocados, also adorned with crowns. So high resolution, low cost. So let's continue to talk about image editing. So image editing with diffusion model is pretty powerful. So for example, here we want to give some input strokes. Here a tower a room, and now we want to gradually recover and generate a tower and a room by denoising, and it should be match the input stroke. And how do we do that? So these are separate spaces. One is the stroke, one is the image. They are in different locations. So what we do is we can perturb them with noise. So adding noise to the stroke such that the noisy image can have some overlap with the original space. And then we do the reverse process to gradually denoise. We can move this blue dot closer and closer to the center of the to the green region, okay, which is the image region, image space, so that the output look like a castle in this case. So this is some example given this original. This is drawn probably by a human, and then we give a prompt, a fantasy landscape trending in ArtStation, and this is the generated image given the input stroke. We also want to personalize the model, okay? Not only edit the model, but also personalize the model. Say, given a dog, we want to generate some dog swimming, sleeping in the bucket for this particular dog, right? It has gray hair, large ear, and white legs. We formulate exactly the same dog, follow exactly the same dog. Like getting a haircut. This is not a random dog, but we want it to be exactly this dog. And how do we do that? Actually, this is pretty challenging. For example, if we input a few images of this clock, the same clock in different setting, the generated image can have very poor fidelity, like this clock no longer look like this one. The color 3 should be yellow rather than white, and also very few context. They are both white background versus less fidelity, but able to generate new context. The 3 has changed versus both having good fidelity and also diverse contexts. And DreamBooth achieved this functionality by fine-tuning the model. So we can, we're given a text-to-image model, given a few pictures, like 3 to 5 images of the dog, plus the dog itself, the language dog, and passes through the DreamBooth to fine-tune that to get a new personalized text-to-image model and this unique identifier V, and then we can say a V dog is in the beach. It will generate this particular dog in the beach. A V dog walking on a colorful carpet, and then we can generate this personalized V dog to the carpet. So the limitation here is that when fine-tune the model, it's specific is to only one subject. So if you want to generate like a person, like a friend playing basketball, you have to do the fine-tuning again for your friend, and which is costly. If you want to interested in training-free methods, there's plenty of publications later using training-free methods to customize, to perform personalized image generation. Okay, now let's switch gear to talk about fast sampling technique, denoising, diffusion, implicit models. So denoising process is an iterative approach, right? From the noise to the data. The idea is that can we use fewer steps to have a larger stride to reduce the number of iterations? Okay, so previously the method is Markovian. So each xt is only dependent on the previous time step. We train the model such that we only use these properties to the training, but at inference time, can we find a non-Markovian forward process to accelerate it by reusing the same model during the training time? Okay, so we want to make sure the xt minus 1 is not only related to xt, but also related to 0. Can we find such a setting that we don't have to change the trained model, but just change the inference, change it at the inference time? Actually, we can do that. This is the conclusion. So previously, xt minus 1 is related to xt, but now it's related to not only xt, denoted in epsilon, which is related to xt, but also related to x0. Okay, and we can estimate 0 with this equation. So in that, we can have a larger stride time stamp from 0, 10, 20, 30, 1,000. Previously, we just make one time step increment. Now we can make the increment of 10 to accelerate the denoising process. And the original DDTM, if you reduce the number of steps from 1,000 to 20 to 10, the FID will explode. But using DDIM, the FID stays very stable until like 10 or 20 steps. Still, 20 steps still below 10. This is on CIFAR 10 dataset. This is on the CLAB 8 dataset. The FID is both well maintained, while having much fewer sampling steps, like 20 steps, opposed to 1,000 steps. Another approach to reduce the number of steps is by using distillation. So this is a 4-step model. We can distill that such that a single step in the student network can do the same as 2 steps in the teacher network. Okay, we can do another generation of distillation such that the student, which is can directly use 1 step to model what the teacher have done in 4 steps. Okay, so we can distill a deterministic sampler to the same model architecture. And each step, the student model is learned to distill from 2 adjacent sampling steps from the teacher. And every new student will reduce the number of sampling steps by 2. So in this way, we can reduce the training steps, but the FID stays much lower compared with the DDIM, the original non-distilled version. Okay, chapter 3. Now let's talk about acceleration techniques for diffusion models. Let's start with using sparsity. We can exploit spatial sparsity to accelerate the inference of diffusion models, in particular for photo editing. The vanilla diffusion models waste many computations when we have to resynthesize the entire image, even if we only edited a very small portion of that. Say, in this case, we only edited 1.7% of the pixels. You can tell where did we edit. We only added a sun right here, that occupied less than 2% of the pixels. But the original stable diffusion has to go through the entire model and run do convolution on the entire input image. Okay, but spatially sparse inference is basically saying we can just change whatever we edited. For the not edited region, we just reuse the feature map from the original model. Okay, since we only edited the sun, we only recompute the sun in green here and reuse the feature maps for the rest of the areas for the previously generated image. And as a result, this can save 8 times the computation. So this is how it works. So we build this spatial incremental generative engine. SAGE incremental means only change the pixels that has been edited. For those pixels that has not been edited, we just reuse whatever it was from the previous approach, from the previous iteration. Okay, so given the original image, and we drew some piece of cloud on the top, and this is the difference mask, we discretize that to 4x4 grid in this case, and highlight the areas that has been edited. So this is the original image. This is the edited image. So we only gather these pixels, these chunks that has been edited, and then only pass it through the convolution for this edited part. Okay, and we scatter this to the original feature map to get the updated feature map. So that's the one layer of the SAGE, which only do compute, which only do convolution on the edited blocks. We call it active blocks. And we stack them to the batch dimension, so it's easier to parallelize. No sparse kernel is needed since each patch is still dense convolution. And this can also apply to diffusion-based transformers. And we applied it to image inpainting. So what is image inpainting? So we can draw a box in the image, inside the image, and we can paint whatever we want to the box. Now we want to paint a horse, a photograph of a horse on a grassland. Previously, there was no horse. Now we drew a box and we want to place a horse right here. Without this approach, we need to generate the entire output image, which takes a lot of compute and pretty slow, 300 milliseconds. Now we only added the masked region, okay, which is 3 times faster, 4 times faster, and the quality match very well with the original input. So this is another example. We only edited 3% of the pixels, added a coconut tree. So this is the baseline model. This is our model. The generated quality is pretty much the same while being more than 4x faster. So this is the real-time demo showing that this technique can enable this interactive photo editing. For example, adding some cloud to the image. Okay, now let's switch gear to talk about applying quantization to accelerate diffusion models. So we've talked about quantization, using quantization to accelerate large language models, but large language model and diffusion model have a lot of difference. For example, on single batch inference, large language model is bottlenecked by the memory bandwidth, while the diffusion model is bottlenecked by the compute. So those methods like weight-only quantization cannot accelerate diffusion models because they're compute bounded rather than memory bounded. If it's memory bounded, large language model can benefit from like W4A16 weight-only quantization. But in order to achieve measured speed up for diffusion models, we need W4A4 quantization, quantize both the weight and activation to only 4 bits without losing fidelity, which is even more challenging than W4A16. And let's see how do we solve that problem. So we observe the weight and activation both have a lot of outliers in diffusion models. We have seen this figure, sister figure in smooth quant lecture. So this is the distribution. So the green is a 50% percentile, the yellow is 99 percentile, and the remaining is the rest 1%. So the red part is the outlier. So the activation has a lot of outliers right here, and the weight also has a lot of outliers, which making it both difficult to quantize. So we can apply smoothing like we did in smooth quant to migrate the quantization difficulty from the activation to the weight to the activation. Is much smoother, a lot less red compared with here. But the activation has more outliers. Previously has only 1 outlier, now it has 2. This is a real distribution, a lot more red compared with previously. But luckily, the activations outlier is migrated. So we just need to migrate the weights outlier. We can do that by decomposing using a side branch, which is a low rank branch, to absorb those outliers using full precision. But this is a very low rank, only 32 ranks, so this is very cheap. So we can migrate the outliers, migrate the quantization difficulty to the side branch, such that after SVD, the weight has a lot less outlier compared with before. So finally, both the weight and activation are 4 bits, but it's very easy to quantize. There's no outlier and associated with a very low rank side branch. And the good thing about this approach is that if you use LoRa fine tuning, you don't need to re-quantize the weight, but you just need to append a few more ranks, like 16 or 32 more ranks in full precision by whatever LoRa you want to add to this module. Since a lot of people are using diffusion models with LoRa, so this is very compatible with the framework. Before that, despite that, we actually observed naive implementation lead to a lot of overhead, like the yellow and the red region for this up and down projection due to due to the LoRa branch. So this is the main branch. This is the LoRa branch. We fused such overhead such that the latency overhead, 40% latency overhead is removed. And we achieve that by actually fusing this down projection with the previous kernel, since they share the same input. And we fuse this up projection to the next layer, 4-bit compute, since they share the same output. Okay? And in that way, we can reduce this overhead in red, in yellow. So this is the kernel fusion. So this is the speed up and the model size reduction. So the speed F16, we can reduce it by 3.6 times. For the W4A16 method, the conventional NF4 can also reduce the model size and also reduce the memory. We can reduce a bit more since we're also quantizing the activation. However, this is the beautiful part. Okay, so this is the exciting part where the conventional W4A16 work can only reduce the memory, but it doesn't lead to any speed up. It's actually slower because they still need 16-bit arithmetic. But here we can use 4-bit arithmetic, either int4 or FP4, and can achieve more than 3 times measured speed up on 1490 GPU. Okay, and this is a single-step latency. The baseline method is out of memory. The NF4, we can make it a 3.5 times faster than the NF4 approach. So this is the visualization comparing the baseline approach. It's out of memory on a 1490 GPU. Okay, and this is NF4, very high fidelity, but it doesn't have any. It's still more than a second. It's pretty slow. Well, we can make it just half a second. This is the naive interval quantization. So the quality is really poor. Actually, the quality already started to degrade from IP16 to NF4 approach. But our approach can well maintain the output quality pretty much the same as the original input. Well, the memory is reduced. Previously 23 gigabytes, now it's only 5 gigabytes, half a second compared with 1.8 seconds. And this is showing that SVD quant is very compatible with the existing LoRa. We can just add a LoRa branch without having to do any requantization. Okay, so this is IP16 and our info version using different LoRa models like realism, pretty much the same. The anime, children, yarn, different kind of styles, well maintain the fidelity for different LoRa models. Finally, we can apply parallelism to exploit multiple GPUs to accelerate diffusion models. For language model, we talk about we can use tensor parallelism to accelerate it by throwing more GPUs. We can just make it faster. What about for diffusion models? How can we throw more GPUs to make it run faster? So these are 2 devices. We have 1 GPU on the top, 1 GPU on the bottom. We wanted them to work together to generate the image fast. However, these 2 models have to communicate, okay, to do the attend to each other, which will lead to large communication overhead, which we don't want. It will also negate the saving we may get from multiple GPUs. So we want to reduce the number of communication. The insight here is that the input across adjacent time steps are actually very similar. So the input here, the input here, they are very similar to each other. So rather than directly communicating, we can actually communicate using the stale activation for those communication. When we are attending to each other, we can attend to the previous time step. That's totally fine. That's the insight. And we can exploit that to reduce the communication overhead and also enable the communication to overlap with computation since we are reusing the old time steps feature map. So originally the latency is 12 seconds with 4 GPUs. Naively doing such parallelization indeed make it 4 times faster, but it will generate 4 separate images. due to lack of communication and the duplicated subjects. This is naive parallelization across 4 GPUs, but using the distributed diffusion, we can make it 3 times faster, but the generated image quality is very good compared with the original one, rather than generating 4 separate images separately. So this is the speed up across 1, 2, 4, 8 devices. It's about more than 2x for 4 devices here. On higher resolution, the speed up is even higher due to the communication overhead is saved. With up to 8 GPUs, so at a 3K generation, it's about 6 times faster. All right, so here's the summary for today's lecture. We first introduced the basics of diffusion models, and then we talk about how to add condition, how to diffuse in the latent space, including using deep compression autoencoder to compress the tokens, how to perform image editing and personalization. And then we talk about fast sampling techniques, DDII, and distillation, together with acceleration techniques using SIGE, the spatial sparsity, the SVD quantization technique, and also distributed diffusion by using parallelism. That's all for today's lecture. Hope you have a happy long weekend.